Hello everyone. Welcome to our series on the derivative of functions. In part 1, we're going to be talking about the concept of the derivative, and that's going to lead us to the definition, the mathematical definition of the derivative. Okay, the concept of the derivative starts with a line. Why a line? Well, we know how to calculate the slope of a line. I can take any 2 points, like these two, figure out the change in x, also called the run, and the change in y, also called the rise. Then the slope of the line is equal to the change in y over the change in x. Basically this number divided by this number for these 2 points. Now, no one's going to tell you, well, you have to pick these 2 points. You can't pick these 2 points. They're never going to tell you that because that's completely wrong. It doesn't matter what 2 points you pick. You could pick these 2 points, and even though this change in x is different than this change in y compared to these two, the ratio is going to be the same. That would be true for these 2 points as well. So it doesn't matter what 2 points you use, as long as they're both on the line, you're going to get the same slope. The slope of a line is the same everywhere. What about a curve? The derivative is really all about extending the concept of slope to curves like this one. It's a nice classic parabola going through the origin. And we're only going to use the positive half of it, so that's why I've kind of lopped off the rest of it. Poor parabola. Let's say we're interested in the slope of this parabola at the point 1, 1. Well, first we have to kind of define what we mean by slope of a curve. Now, I imagine being a person walking along the x-axis. Maybe you're only this high, let's say. You're walking along the x-axis. Just before you get to the parabola, you're walking on flat ground. Your slope, effectively, is 0 because the slope of the x-axis is 0. Now you start walking up the parabola, up until you get to this point. What do we want to think of when we think of the slope of the parabola at this point? One nice way to think about it is what direction is the person going in when they get to this point? If you imagine like a straight line motion, they're going kind of like this. I'll try to draw that in the next slide. Here we go. This orange line here represents the direction of motion of this person when they get to this point. Just like that. That direction is what we want to think of when we want to think of the slope. Now, of course, for slope, we need a line. So I'm just going to overlay a line right on this direction arrow, just like that. This line has a special name, and it's called the tangent line. This line is special. It goes through the curve at that one point that we're interested in, yes. But notice that around that point, the line becomes essentially indistinguishable from the curve. The line is essentially infinitesimally close to the curve, even though it doesn't actually hit the curve except at this point in this region around the point. It's not actually hitting the curve right here or right here. It's just that we have to draw lines with a certain thickness, so it looks like it is. Essentially, the tangent line is the line that best approximates the curve around our point. And we want to use this to represent the slope of the curve at that point. So the question is, how do I get the slope of this line? How do I even get the equation of the line? I only know one point that it goes through. So that's really our challenge for today, is to try to figure the slope of this line out somehow. One way we might do it is connect a line from here to any other dot further up the parabola. So I've drawn one in. And again, this point up here at 2, 4, I could have picked any point. I just happened to pick 2, 4. And I've drawn my blue line. This also has a special name. It's called a secant line. That's this nice little blue line right there. we know how to calculate the slope of this line. We just take the change in y for these 2 points and the change in x for those 2 points. And if you do that calculation here, you're going to get that the slope equals 4 minus 1 over 2 minus 1. That's equal to 3. That is the slope of our secant line. Now you're probably thinking, okay, that is a completely different line than the orange line. But wait, what if I move this dot a little bit closer to this dot? Okay, here we go. Here's another secant line. Compare this line with the one we just had. This line is actually closer to the orange line, isn't it? Let's calculate the slope of the new secant line. Use the same process, except now we have to use these 2 dots. Remember, this is still y equals x squared, so if we're at 1.5, our y value is 2.25, that's 1.5 squared, minus 1 all over 1.5 minus 1. That's the slope of our second secant line. Okay, that's not a hard calculation. You're going to get 2.5. So the previous secant line had a slope of 3. Our new secant line has a slope of 2.5. Why not continue this process? We know that this line seems to be getting more like the orange line as I slide this dot further down. I'm keeping this dot the same, but I'm moving the second dot. Let's try another one. Okay, I've moved this dot down to here now at an x value of 1.25. Look at how close this secant line is to the orange line now. Here's the previous. Here's the third one. Great. Let's calculate the slope of this secant line. Okay, this is at 1.25. The square of that is 1.25 squared. Turns out to be 1.5625. Subtract the y value of the first dot, divided by 1.25 minus 1. Easy calculation, you get 2.25. So we started with a slope of 3. We moved the dot down, slope of 2.5. Move the dot down again, slope of 2.25. If I had to take a guess at this point, I would say that the slopes seem to be approaching the value of 2, and I'm kind of hoping that this orange line has a slope of 2. Now, I've used the word approaching here, and that might ring a bell. When we talked about limits, we talked about values that approached another value. Never quite getting there, just approaching. And it's important that we never quite get there in this case because we need 2 points, this dot and some other dot, to calculate the slope of the secant line. So let's take that calculation one step further. Okay, so here we are. I'm going to calculate the slope of a secant line between this point and this point, but instead of calling this a number, let's just say that it's the value 1 plus h, where h is some variable that I'm going to make go to 0. I'm going to make this number really small. That's going to make our secant line get close to the tangent line. Okay, what's my y value up here? Well, since the function is x squared, my y value is 1 plus h quantity squared. Okay, so the slope of the secant line is change in y. Well, that's 1 plus h quantity squared minus 1 all over the change in x. The change in x is 1 plus h minus 1. Well, that's just equal to h. Let's simplify that a little bit. If I FOIL this out, I get h squared plus 2h plus 1, subtract 1, that 1 is going to disappear. Okay, one more simplification. I'm just going to divide top and bottom by h, and I get h plus 2. Okay, that is the slope of the secant line between here and here. But remember, we want to squeeze this dot, this upper dot, toward this one. We're going to make this dot approach this one. How do I do that? I take the limit as h goes to 0 of my slope. That's going to give me the slope of the tangent line. And this is a really easy limit to calculate. It's just equal to 2. That is going to be the slope of our orange tangent line. It's actually the slope of the line that we looked at in the first slide. I had to take a limit because we wanted this upper dot to approach the lower dot, but never quite get there. That's what we know about limits. We're never actually getting there. That's why it was actually okay to cancel the h up here. If h is 0, we can't actually do that. But because in a limit, h never quite gets there, it's okay. And we get an answer of 2. And we saw that when we calculated the slopes of the secants, we got 3, 2.5, 2.5. If you continue that, 2.25. If you continue that process, eventually you get 2. Let's try to come up with a formula for the derivative in general for a function f of x using the same process. So this point is x, this point is x plus h, and here I'm not using the number 1 anymore. I want to use a generic letter, x. This is x plus h. So this y value must be f of x. This y value must be f of x plus h. Now we can write a full expression for the derivative. Here we go. The limit h goes to 0. F of x plus h minus f of x. That's the change in y of the secant line. That's what's on top. Divided by x plus h minus x. That's the change in x. Well, that's just h. That's it. That is our definition of the derivative of a function f of x. Next time we'll look at how to calculate the derivative using this definition. I hope that video was useful, and I'll see you next time.